And then we're gonna welcome Dr. Graham Spinks, and he will present online. He is an alumni of the Lear Lab. And his talk is going to be about generating textual and visual explanation of radiography images.
Graham, can you hear us?
Yeah, I hear you. Do you hear me?
Yeah, we can hear you.
Yeah. Okay, good. Let me know if you are able to see my screen.
Yeah, we can see it. Take it away.
All right. So hi, everybody. I'm going to talk about work on justifying diagnosis decisions by deep neural networks. So the goal of this work was to create a holistic system that diagnoses X-ray images with textual and visual justification of the outcome. So what is this justification? It means that if you make a diagnosis for an X-ray, that you explain and you provide evidence to support the model prediction. Now, this was part of the CALCULUS project, and the reason why we did this research was essentially because we wanted to learn how to combine, interpret, and visualize different modalities, right? So in this case, we have the images, which contain X-rays, and explanations about what is being seen in those images, which is the text modality. And combining those two is not straightforward. And so this work was focusing on that particular aspect of that. Now, this has some use cases in the sense that if you could learn how to combine these modalities and interpret them and process them correctly, you could help assist specialists with critical high volume tasks, which in this case specifically is diagnosing chest X-rays, right? You could hope to speed up their work, for example. The data set that we used is this chest X-ray data set from the National Library of Medicine. Now, this data set is not perfect. There are actually some quite well-known issues with ground truth labels. There are also only a limited set of X-rays, only 2,446, which made the work also quite challenging. We decided to focus on the normal and the cardiomegaly diagnosis. Cardiomegaly is essentially a diagnosis for hearts that are too large within the chest cavity. But the diagnosis, the labels for the cardiomegaly diagnosis in this data set were relatively good compared to some of the others. So we focused specifically on this use case. Another thing to note is that the X-rays we used had a limited resolution, which also limits what you can do with them. But for the cardiomegaly diagnosis, that was good enough. So one thing that is often heard is that neural networks are black boxes, right? And what is meant by that is that, okay, we have an input, we pass it through the neural network, we don't really know what it does or how it arrives exactly at its conclusion, but you do get a conclusion, and in this case, a diagnosis. The question remains, how did the neural network arrive at the diagnosis? And which aspects of the input were taken into account? And there is some existing research that shows that, well, neural networks can actually have surprising ways to arrive at their decision. So if we look at this, the first row of images up here, this is a neural network that was trying to classify a particular type of fish that's called a tench. And this type of fish is very often used in fishing competitions as a prize and so on. And so the neural network, instead of looking at what the fish looks like, it actually looked whether it would find fingers that are holding up a prize fish in the image. So it's actually arriving at a relatively good outcome, but in a completely unexpected way, and probably not a desirable way, depending on the application. Similar examples exist below. So if you have a handheld computer, it's actually just looking to see if it finds a keyboard. And if you're looking at book jackets, it's actually, excuse me, it's actually looking at letters to determine whether this is a book jacket. So these things are not exactly as expected. So what is the typical way to explain how neural networks arrives at its decision? But one thing that is very often used is something called saliency maps. And in this example here, excuse me, in this example here, we see that we have an X-ray that is, in this case, showing cardiomegaly. So this is the heart size in this X-ray would be too large for the cavity. And then the saliency map method essentially shows the parts of the image that were focused on by the neural network to arrive at its decision. So in this case, it is looking more or less at the outlines of the heart here and there, but it's not super clear exactly, why it says this is cardiomegaly, right? So we decided to work on a different approach, and in this case, what we needed for our approach, we decided to start with smooth, continuous representations for text, right? To generate such representations, we used a neural network setup that is called ARAE, an autoregressive autoencoder. And essentially how this works is the following, right? So in the bottom, you see that there's an encoder and decoder, right? So it learns from a caption, an original caption, like the one you see here, HCLCT chest showing left upper lobe, etc. You pass it through the encoder, you create an embedding, a vector embedding, and then you decode it again to reconstruct the original, right? And you see maybe it's not always perfect, but you get quite close to the original one. But at the same time, we are training a generator from random noise to generate similar fake embeddings. And at the same time, we're training a discriminator to determine whether an embedding is fake or real. And if you take this whole setup and train it at the same time, what you essentially get is a representation space for these embeddings that is continuous and smooth. And by that we mean that that the meaning of similar descriptions lies close to each other on this representation space. So that if you traverse this representation space by making small changes to the values of a representation, you would actually arrive at a very similar description, or one with similar meaning. Right? So that's what we use to create our representation space to get started for our approach. So let me just pause here for a second on what we mean by a continuous representation space, right? So if we take as an example the sentence enlarged heart size, there are two main ways to represent it. The first one is a discrete representation, and the other one is a continuous representation. The discrete representation has ones and zeros, so that means if you a change of 1 here, you actually jump from a 0 to 1. It could actually have quite a drastic change in the meaning. It is, however, more interpretable. If these dimensions have a particular meaning, you could interpret this quite well. Now, the continuous representation space looks like this, and it means that any small change in any of these dimensions will help you traverse the representation space. But it could also be quite meaningful, right? It means that if you train it with a neural network, you could have gradient updates that make small changes to this representation, and it actually moves the representation into a meaningful, different part of your representation space. So concretely, if you have this large heart size sentence and you just say large heart, well, those two representations in a continuous representation space will be very similar. Okay. So what is our overall approach to achieve what we want? So as a reminder, what we want to achieve is we want to have an input X-ray. We want to provide a diagnosis for it, and we also want to provide a justification for that diagnosis, right? So let's focus here on the first part of our approach, where essentially the input is a real X-ray. Pardon me. So the input X-ray, what we do is we perform a mapping to a representation R. This representation is the smooth, continuous text representation that we just talked about on the previous slides. Now, the next thing that we do once we have this representation is we map it to text. And that is essentially our method to give a textual justification. So this representation is then mapped to something that says, this is a normal chest X-ray, and we don't see any issues in terms of diseases that are visible in this image. That could be our textual justification. So essentially, we are using the decoder from our ARAE setup before to map this continuous representation to this diagnosis and caption, right? Now, how do we get the input image to this representation space, right? So this is this mapping I that I'm talking about here. To do so, we have our input images and we train the convolutional neural network to map to this continuous representation space. We also have our decoder from our ARAE that is able then to map it to reconstructed captions. We are not training the weights for this mapping in this setup. We are only training the convolutional neural network to map it to a correct location in the continuous representation space. Now, let's now focus on the next part, right? So once we have our continuous representation R, we want to map it to an alternative representation R accent. And the way we want to map it is quite important. What we want to do here is actually what we want to say is we want to map it to a representation that belongs to an alternative diagnosis, right? So if the diagnosis here was normal, let's say we want to map it to a diagnosis of cardiomegaly. But we want to do so in a way that the meaning of the sentence of the justification is quite similar to the original. And we also want the representation of the image to be quite similar to the original, right? So how can we perform this map, right? Well, essentially we're traversing the representation space, but we are constraining it with several losses. And we have three different losses that we're using. The first one is saying, well, when we map it to this alternative image, let's make sure that the diagnosis is not the same one as the original one. So we make sure that we're not mapping from a normal image to a normal image. We're assuring that we're mapping from normal to cardiomegaly, for example. The second constraint says, well, if we map to this alternative representation, we want to make sure that if the image that belongs to that representation is quite similar to the original image. We don't want to map to something completely different. We want it to still have the main outline, the same outline, the same visual cues as the original. So that's what this second loss does. And to do so, it uses a generator. This generator essentially maps the representation to an image and compares it to the original image. Now we'll explain later on how we get this generated. Okay, but for now, that's enough to understand. And finally, we have a third constraint, which talks about the embedding simulator. And essentially, this is just saying, well, these two representations, let's make sure they're not too different. And if we put all of that together, we have a total loss for our mapping. And so we traverse the representation space and optimize this such that the loss is ideal, optimal, right? So that means that now, okay, we have our input image, we have our representation that we get from there, we have our diagnosis and our caption, and we're able to map it to this alternative representation. Now, the thing that we get for free here is, well, this alternative representation, we can actually map it to this alternative diagnosis and caption that belongs to that, right? But this part is still not clear, right? So once we have our alternative representation, how do we get to the nearest generated X-ray for this alternative representation? So to do so, we trained a generative adversarial network, and more specifically, we trained a StackGAN model, right? So at the input, we have our representation that is coming from the ARAE, as we said before, a continuous representation. We feed that to the stage 1 StackGAN, and at the output of the stage 1 StackGAN, we get a low resolution output image of the X-ray, right? And that's not enough, though. We want to have a high resolution. So therefore, this image is fed into the second stage together with the original text representation. And this second stage essentially blows it up to a higher resolution such that we can see some visual representations in more detail. So that's how we arrived at the method to go from our alternative representation to our nearest, to the image that corresponds to this nearest alternative representation. So I think all of this will perhaps get more concrete with an example. So let me first focus on the first column. So what we have at the input of our entire system is an X-ray, right? So this belongs to a patient, and we feed it into our system. And as output, what does it give? It gives a diagnosis. In this case, it says this X-ray is normal. There's no disease, right? And it gives a textual justification. It says there is no focal consolidation, no pleural effusion or pneumothorax. All right, so that's the justification for saying this is a normal X-ray. And now the extra justification that it gives is the counterexample visually, right? So it says, well, this is the reconstruction that we are seeing of the original X-ray. So in the representation space, this is what this original X-ray looks like. And now it's saying, okay, but so if the label was not normal, if this was actually a patient that had cardiomegaly, well, what would the X-ray look like, right? What would the image look like? And that's what you see here in the last row. And you see here that indeed the heart size has become a little bit larger compared to the original one. And it's saying essentially where it's saying, you know, where this switches from a normal to a cardiomegaly X-ray is right here, right? If the R size were any bigger than this, we would call this a cardiomegaly diagnosis rather than a normal. So it's kind of explaining visually why it arrived at the original one by providing a counterexample to the original diagnosis. Now let's focus on another example, the one in the last row here. So in this case, the diagnosis is cardiomegaly, which does not correspond to the ground truth. The ground truth was normal. Now I'm no doctor, but for me personally, this actually does look like a cardiomegaly X-ray. Now, to better understand why it arrived at cardiomegaly, we can then again look at the textual justification. So it says cardiomegaly, no acute bony abnormality, lungs are clear. So it essentially says we're seeing cardiomegaly in this image. And then we again look like, what does this image look in the reconstruction space? And it shows this one here, right? And it's saying, well, if it weren't cardiomegaly, what do we think it would look like? And that's what this last image is. And you see again that the heart size has decreased compared to the previous image. And so you see, even in the cases where, you know, perhaps the diagnosis doesn't agree with what the human says, well, this justification could be useful to explain why it arrived at that diagnosis. Could be a check for the human specialist to make sure that everything is actually correct with what they performed. Now let's analyze the results from a quantitative perspective, right? The first thing we're looking at is the representation space. So there's sort of smooth representations that we learned with the ARE. You know, we want to make sure that they work well. And one of the ways of analyzing is by saying, well, if we use these representations rather than just a simple neural embedding layer, and we generate images from them, the quality of those images are better, right? And that's essentially what this first metric says. The Wasserstein estimate, it says, well, with the ARE, we are getting better images, visually more preferable images to the simple neural embedding layer. And we also create an alignment estimate for this work to make sure that the images correspond to the caption that were used to generate them. So again, we see that the ARE embeddings are better than the simple neural embedding layer. So a lower value is better for both of these metrics. And there's a significant difference, right? So that means that these ARE embeddings are indeed preferable to just the regular embedding layer. With respect to the diagnosis, we also want to make sure that we are getting accurate diagnosis from our holistic system. So we compared it to some state-of-the-art single task methods, meaning they're just some neural networks only trained to perform a diagnosis from the chest X-ray. And we see that our method is quite competitive with a lot of the state-of-the-art single task methods that exist out there, right? So that is quite a desirable output as well. Next, let's look at the captioning, right? So when we provide our textual justification, we want to make sure that the captions that we generate are also high quality enough to actually be usable by human operators. So we also compared to a state-of-the-art method at the time for a single task captioning method, and we actually see that our method outperforms on a lot of the metrics that we used, which are some of the metrics that are standard used in those cases, except for the CIDR metric. All of these were performed over 3 runs and taking the average. Now, I think perhaps the more important part or the more relevant part for this work in particular was, well, does the presented evidence actually help explain why the diagnosis was put forward? So that's the first question you're seeing here. And all of these questions that I'm about to detail, we asked them to some human experts, right? Some human radiologists. to 3 of them, and we gave them a large size each so that they could all evaluate these questions on some samples coming from the output, right? So this is the first question. We also checked the second question, which is, does the network appear to have a correct understanding of which parts of the X-ray are important for the diagnosis? The third question was, do you agree with the proposed diagnosis? And the fourth is, how certain are you about the final diagnosis? And if we look at the results, we see, if we compare to the saliency method that we showed before, we see that our method significantly outperforms on the first 2 questions in terms of justification and understanding. So what we're really seeing here is that this multimodal approach that combines text and images, that uses a multimodal representation space in a way, it is able to provide a benefit at the justification stage for this particular task. It means that we can get a benefit from using this multimodal approach because we're getting significantly better results when providing justifications to human experts. Now, for the third and the fourth question, we saw no significant difference, which essentially means that both methods arrive at similar diagnosis and performance, and it doesn't particularly improve the human certainty one or the other, right? So there's no significant difference there. So I think that brings us to the conclusion. Essentially, this justification technique performs significantly better than the saliency map method. And we also arrive at similar diagnosis and image captioning performance to single task state-of-the-art methods by using this multimodal holistic approach. And the results suggest that taking such multimodal approaches could actually be interesting avenues to improve human-computer interactions, in this case for medical diagnosis, but also for other tasks where human-computer interaction is critical. And that brings us to the end, and I would like to open the floor for any questions there might be.
Oh. Yes. Thanks very much for the talk. Do we have some questions for him? Okay, so I got a question. I'm really curious. Do we already see some practical application of such kind of methodology in hospital?
So I'm not aware of any hospitals already using this kind of approach in a practical setting. And I think the reason for that is that a lot of this is very new still, and any application within a medical setting will run into a lot of barriers, legal barriers, data concerns, and so on. I do think that as years go on, very soon we'll start to see more and more these things being used in a practical setting. But as of now, I think it's still quite limited. But then again, I haven't been following up on the latest, the most recent years to know whether any of this has been used in a practical setting.
All right. Okay, so I've been actually working with neuroimaging, like fMRI, MEG, EEG. It is also like one sort of medical images, I guess. So do you think that, I saw that you're working with X-rays. So do you think like it is the methodology itself is compatible with other kinds of medical images?
So, I mean, I think so, right? There's nothing stopping us from applying this technique in principle to other settings. Now, of course, there might be practical barriers, right? So, for example, MRIs is something I looked into when I started this research, but the resolution tends, the resolution that you need to consider tends to be quite high, I believe. I also had trouble finding good data sets at the time. I'm hoping that's better for you now. But essentially, there are practical barriers, right? If we had the right data sets, the right computing power, and so on, in principle, these types of techniques could extend to any setting. It doesn't even have to be medical, right? It could be anything where we want human-computer interactions.
Okay, yeah, very interesting. So, any other questions? Oh.
Yeah, so your embedding space is a single vector. Is that
Correct.
a problem for the complexity of the justifications you can handle?
So that's a pretty good question. I would say that that is still a part of the approach that would need improvement, right? So while at the time, I think the ARE embeddings were probably one of the state-of-the-art ways of representing, you know, to getting a smooth representation space. I think a lot of work has been done in the meantime to have better alignment, also using perhaps videos in the, images in the embedding space, whereas the embedding space I used was text only, right? So I think improving the embedding space would probably be the path forward to improve this approach significantly. And you could even imagine using, for example, at the moment, pre-trained embedding spaces, such as the clip encoder from some of the diffusion models. I'm not sure on how many X-rays they've been trained, but I imagine that there might be some part of the data set in there that also contains them. And maybe that would even out of the box work better than the approach that I was using at the time. So that might be interesting to follow up on, for sure.
Thanks.
Hi, I missed the beginning, so I'm sorry if you went over this, but I'm wondering, from your perspective, what makes one explanation better than another explanation?
So, okay, that's a good question, and it's hard to answer, right? Because I think part of the reason why I performed this research was because I had this intuition that just text for an explanation is not sufficient, right? In a lot of settings. And I think that's why, you know, there's also been this exploding growth in terms of, you know, multimodal models in recent years. And you see it, for example, with ChatGPT, you know, explaining complicated subjects could be made a lot easier by including images. Now, I don't think it's as easy as saying we always need images, right? It really depends on what we're talking about. But in a lot of cases, just the simple fact of adding an image that shows what one thing is and the other thing is could just really simplify things for an audience, make it faster to understand and better to understand, right? How are you going to capture the details of what is a normal X-ray versus a cardiomegaly X-ray just with text is very hard. So that's why I think, you know, images are crucial for a lot of applications. Does that more or less answer your questions?
Yeah, I was also wondering within the modality, like let's say vision or language, there's different levels of abstraction at which you can provide an explanation. Even in images, you know, you can have a line drawing or something that's very detailed. In language, you can have a summary at different levels of abstraction as well. And so do you think about that as well in the work?
So in this work, I don't think I took a lot of that into account, just because at the time it was quite new, right? This idea of just even providing a counterexample. But I think that could be a growing topic of research, and I think it already has been in the past years, because the nature of this humor-computer interaction is not straightforward, right? Like, what makes it something easy to understand for a human? How do you even put that into words or constraints and so on, right? So I think it's a very good question. I think it's right on the nose about where future research might take a lot of these things.
Thank you.
Okay, so no more questions. Thanks again for the very interesting presentation. And so the session for the morning has come to an ending. And just a kind of reminder that we are going to have lunch and poster session till 1:30 in Maschinensaal. Yeah.
De Maschinenzaal is in the Technothermis Institute, I think. But if you just follow us, for those of you who don't know where that is, just follow. It's not so far. It's a few minutes, but I think it's maybe you can put on a coat. Yeah, we have to go outside.
That's a good point. I don't even know myself. But she will be here the entire day, she said, so she'll get instructions.